All right, we're into the bonus examples. So these are examples from the textbook Cengel. And very similar to the one we did out of Borgnacki. Borgnacki? I can't remember how to pronounce it. Anyway, we have determined the specific volume of refrigerant 134A at 1 megapascal and 50 degrees Celsius using the ideal gas equation of state, the generalized compressibility chart, and compare with the actual value of 0.021796 cubic meters per kilogram. All right, sure, we'll do that. All right, so I think I actually want to look this one up first. So let's take a look at the temperature is equal to 50 degrees Celsius. By the way, let's go ahead and turn that into Kelvin right away so we don't forget. And the pressure is 1,000 kilopascals. 1 megapascal. So 134A is, first off, let's start right here in B.5.1 and come up to 50, and we see that we get 1,318, and we're at 1,000, so we are less than that, and therefore, look at those nails, that's kind of disgusting. We are therefore superheated, right, because this is the saturation pressure and temperature. So we can go over and find at 1,000 kilopascals, 1,000 kilopascals, and we can find, here we go, 1,000, and they said they had 0.021796. So we are off just by ever so slightly. But interesting that they have a different value than us, right? But let's continue on as they told us to do. So first, we want to go to the ideal gas law. We need R, which is going to come out of table A.5. And we are looking for 134A. 134A. And here is R. We just did this in the other problem. 0.08149. Kilojoules per kilogram degree Kelvin. We also know that we're going to need, but well, let's just do it right now. We'll just keep going. So the specific volume is going to be RT over P, right? We're okay writing that because we did know that PV is equal to RT, or PV is equal to MRT, right? Either way. At this point, we could probably write that. For R, I'm going to turn this into Newton meters. So I'm going to go multiply this by 1,000. So now we have Newton meters per kilogram degree Kelvin. And the temperature was 323 degree Kelvin. And divide by 1 million, because we have 1,000 kilopascals. So 1 E6 Newton per meter squared. You do all that, and you get 0.02632 cubic meters per kilogram. If you wanted to prove that to yourself right there. The Kelvin goes away, the newtons go away, and we're left with meters squared times meters. There's your cubic meter per kilogram. So there you go. And if you're going to compare this with the one up above, you would say 1 minus 0.02632 divided by 0.021796. And I believe this one is, I think it's going to be a negative number. I think you get a negative 20.76% error. Right? So let's go to the other guy. So what we're going to need is to use the generalized tables. So we need the critical temperature. And let's see, I need to write what table I use, right? We're going to use A.2. And A.2 for that refrigerant, which is all the way down to the bottom. It's going to have a 374.2 degrees Kelvin right up at the top. Oh, that column and that column is the one we're doing it down here. There's your critical temperature and there's your critical pressure. So the critical temperature is 374.2 degrees Kelvin. Critical pressure is 4.06 megapascals. So the reduced temperature is going to be 323 divided by 374.2, or 0.8629, and the reduced pressure is going to be 1 divided by 4.06, or 0.2463, might as well be 0.25. We need to find the Z. We're going to, let's see, I'll go ahead and do it through this, right in here. All right, so the TR is close to 0.85. Interesting. Someone just did the thing at 235. Weirdo. Okay. And 0.85 right here. And then we also need to see where that crosses 0.2. So I gotta put this in here. 0.2463. Boom. Right in there. Oh, look at that. It's pretty damn close, actually. I would say it goes up a little higher. Say 0.85. Yeah, that looks like it crosses. Here's 0.85 right there. That right there, 0.85 crosses. And so I'm going to say that's what the right answer is, 0.85. 0.85. So if you want to find this V now, we write Z times RT over P, right? Because, well, the equation is Z is equal to PV over RT. So you want V. You'll rearrange down to this. So 0.85. We don't need to put the units in. We got them correct. And basically, all the things are the same up here. So we could just multiply this by the thing we just got a second ago. 323, but I'm going to go ahead and be overly detailed. It's a professional hazard. We get 0.02237 cubic meters over kilograms, and make a comparison. Percent error. Well, it should be 1 minus 0.02237 divided by 0.021796, and we find we We still have more here, so I think it's going to make it negative. It doesn't matter. 2.65% error, which is pretty acceptable most of the time. I wish this example had used a different material because we had done this in a previous example, so it's really not all that much different. And see you in the next video.